Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Our next speaker is Frank Fenning, who's both Jeanette's replacement as a department head, but also been involved since the earliest days in how to rethink introductory programming courses to incorporate more, let's call it, logical thinking.
Okay, so I'm going to talk about another one of these two main courses that anchor the new curriculum that Randy was talking about, which we call 122, which is called Principles of Imperative Computation. So, but I've talked about this several times before. The kind of thing that I wanted to emphasize at this point is some of the origins of the idea. And actually, turns out that MSR and Microsoft played a very significant role in the development of this particular course, in a particular way about thinking about introductory computer science. So for me, actually, what was a very important experience was Manuvir Das from MSR, I think eventually moved to Microsoft Windows team, gave a talk at CMU in 2005 where he talked about, the title of his talk was Software Excellent via Program Verification Analysis at Microsoft. And he talked about the way that program verification, program analysis influences and is central to the development process at Microsoft Research at the time. Now the tool chain that he started or was developing at that time are now part of Microsoft Visual Studio and being distributed. So that was one very strong influence. I'll talk more about this after the first, starting with the second slide. The other thing is that Peter Lee was revitalizing around the same time in 2005, of course, on compiler design. And he was using a safe imperative language that had integrated into it so-called fat pointers. So a fat pointer is a pointer where, together with the pointer itself, you store bounds on what it might become and still safely access memory. So you have a lower and an upper bound for the pointer. You can do pointer arithmetic. And he integrated that into the compiler design course, which turned out to be a little bit overshooting in terms of the students' abilities to actually implement the compiler in a reasonable amount of time. But it was certainly a strong influence of that. And his thought was, wouldn't it be nice if you could use the same programming language in the compiler course that we're using in introductory programming? So I've sort of stored that away, and I thought about that. But at the time, certainly there was no possibility of doing that because we don't have the compiler students implement a Java compiler. And Jeanette, at the same time in 2005, was working on writing and talking about computational thinking. And thinking like a computer scientist, this is a quote from her paper, means more than being able to program a compiler. It requires thinking at multiple levels of abstraction. And I think that was another big influence, and I was thinking about that later on. So let me start with actually what Manuvir talked about at the time. So I actually found his slides. I probably should have got his permission to show some of these, but since he distributed it at the time, okay, here they are. No, it doesn't. Okay. So he was originally a researcher in program analysis, and now he does other things, I think cloud computing, other things at Microsoft. And his claim was that program analysis technology can make a huge impact on how software is engineered. The trick is to properly balance research with a focus on deployment. So it was very important for him that his techniques actually, okay, and he was leading what was then called the Center for Software Excellence at Microsoft. And he was still questioning whether he was doing it well, but at the end of the talk, the audience was convinced. And then walking the walk, so he had this program analysis group that he was heading in June 2005. They filed many bugs regarding Windows. They added 10,000 plus specification to the Windows code base, and they answered hundreds of emails. So they were actually really embedded in the product, which was, like I said, it was a very important thing for him, even though they considered themselves program analysis researchers. So they were not They were not operating system people. And one of the things that he presented during this talk on a much later slide was SAL, which SAL stands for Standard Annotation Language. And he presented as a language of contracts between functions. And he made a very compelling argument at the time that is this what allows you to compose big pieces of software, because you need to specify, what happens when one function calls another, especially if they're done different pieces by different developers in different pieces of a large software system. And so a function has preconditions that must hold when a function is being called. So what does the callee expect from the caller? And a postcondition, which are the statement that must hold at the exit from the callee. And what does the callee promise to the caller about what is being made? And so a typical example would be we have some function which has a return type with some annotation on it that says, more specifically, not just an integer, but maybe a positive integer or something like that. And the parameter t is not just a parameter, but it might be a parameter that must be in certain bounds, a pointer that must not be null, other kind of conditions. And if you specify these and then you enforce them by program analysis or checking, he was saying that buffer sizes, null pointer, memory usage, a lot of the errors that sort of plagued code at that time would go away because you could verify that they wouldn't arise. Unfortunately, he said during his talk, he can't tell us any numbers about how many bugs they found. Okay. But it was very clear that it was extremely effective. And so he also talked about the principle behind SAL, which is that you control the power of the specifications. You must do this very carefully. So the impractical solution would be to rewrite Windows, okay, in a different language so that you can analyze it. That would not work. So what you need to do is you need to formalize the invariants that are implicit in the code already in intuitive notations. And these invariants already often appear in comments. They are in the code. The developers have them in mind. They're not written down, except maybe in comments, but because they're not written down, they can't be checked. So this was his point. If you make them explicit, then you can check those. Okay. And this was exactly these two lessons that I actually took when an opportunity arose a little bit later. So his forcing functions for change, why do we change things the way that they were actually working in Windows development before? Or not just Windows, actually turns a lot of Microsoft products. So if you want to generate bug-free code, or at least code with few defects, there's a sort of a generation of things that people have tried to do that. You can do manual review, but there's too many code paths. It doesn't really work. You can try to do massive testing, but you don't. It's a very inefficient way to detect common patterns of problems in the code. Plus, when you have concurrency, it basically doesn't work anymore. You can try to do global program analysis, but the problem is that the global program is too big, and so results will be stale because you can never carry it out fast enough. You can do local program analysis, but if you try to analyze functions by themselves, they lack the context in which they're going to be executed. And so it doesn't work because you don't have enough information about what the functions are supposed to do. And then the generation 5 is if we just add some layer of specifications, not very much, just in the SAL language, then we can actually do this. Okay. The other thing he reinsured is that it's a myth that developers hate specifications. If you do it the right way, okay, it will actually work. People will actually do it. Now, I tried to transfer this to the students, right? Myth, students hate specifications, okay? So, I had to do the last thing. I had to think like a student, okay, when I was doing the course design. The other one is the myth that theory is useless. And in the whole design of this is actually deployed, and that's sort of the mainstay of software development at Microsoft now. Fundamental ideas have been crucial. Core logic, abstract interpretation, context-sensitive analysis of summaries, alias analysis, the kind of thing that we're actually still working on here now at CMU in the context of this introductory course, were the basis of what he's been doing, and it's extremely important in practice. So, like I said, this was in 2005, and I kind of stored this away as something very, very interesting. Then, many years later, in 2009, an opportunity arose because we were working on a major curriculum redesign, phasing in fall 2010. We were designing a new introductory computer science course. eventually I called it Principles of Imperative Computation. It's based on 3 pillars: computational thinking, algorithms and data structures, and imperative programming. And the computational thinking part, you can see how these things were influenced by Jeanette's and by Manavir's talks and so on. Now this is taken by about 500 students a year. We have only 150 majors, so all the other students are non-majors. They do learn about function pre- and post conditions. They do learn about loop invariants. They do learn about how to reason rigorously about their code. So the guiding principles was that computational thinking and programming should go hand in hand when you learn computer science. The fact that you're not just hacking, but algorithm data structure design is an intellectually interesting activity, a rich activity, and that rigorous types and variant specifications interfaces are crucial. And a lot of these things, like I said, I took away from earlier interactions. So Randy already talked about the role in the curriculum. So this is a prerequisite for a systems class. So we do need to teach imperative programming in a C-like language so that students are ready to take these courses that actually are required in C. At the same time, it's a prerequisite for the course that Guy talked about. So we do also need to talk about algorithms and get them ready for that course. So I broke down the learning goals along various dimensions: the computational thinking, the programming skills, the specific data structures and algorithms that we wanted them to learn, and application contexts. And when I gave this presentation first to the faculty before delivering the course, I think there was some incredulity. People were not believing that I would actually be able to do all of that. But it turned out that it actually worked fairly well, and I think because we stuck to these guiding principles to combine computational thinking and algorithms and programming in one sort of package. So here are some of the computational thinking concepts. A lot of them have to do with different levels of abstraction, which is why I put Jeanette's quote up there. So for example, sometimes you have to reason about your code operationally, how does it actually run. Sometimes logically, what specification does it fulfill, because you might not even have the code. You might only know what it's supposed to accomplish, not what it actually does. Let me skip over the programming skills and the algorithmic concepts. They're actually relatively similar to the kind of thing that Guy was talking about, except no parallelism in this at all. This is very standard sequential types of algorithms. But not, fairly ambitious for first real computer science course. And also important for us was to put it into application context where students could see their code actually in action, doing something that was not just implementing data structure, but actually seeing it in action. So there were some puzzle solving examples, implementing Huffman code. Implementing a text editor is a very interesting kind of assignment. The last thing they do is sort of looking at code as data by implementing a virtual machine, which is kind of the capstone for this particular course. Now, in order to make this work, what I needed to do is design a new language, and we call that C0, which is a small safe subset of C, but extended with a layer to express the contracts, the pre and post conditions for function and the loop invariants. So because it's a small safe subset, it can be garbage collected, so you don't have to worry about problems with memory management. We have only one type of integer, so you don't have to worry about conversions between them. And contracts are not a separate logical language, but simply Boolean expressions that you can run to check whether conditions are being satisfied. And then towards the end of the course, we transition to full C. By that time, students generally have developed some good habits in terms of programming, and they can actually handle that. And then they're ready for the systems course, which was another fairly big influence on me because I actually taught that course 3 years in a row before I started teaching this one. So I kind of knew what students were expected to do in the follow-up systems course after this introductory course. Okay, so the rationale for developing this language was that in this fragment, imperative implementation of simple algorithms are natural, and you saw we can do many examples. The simplicity permits effective analysis. I think that was another very important criteria, that we wanted to be able to do analysis. And the fact that it's very similar to the kind of things that were actually in industrial use. And actually, I had Jason Yang from Microsoft Windows team give a guest lecture in this course the first 2 years in order to talk about what they're actually doing in industry with specifications and how they actually use that in the software development process. And that, I think, was very interesting to the students. One of the most well-attended lectures, actually. So the lecture schema generally, there's this recurring theme that I talk about at the beginning of each lecture, that we really have these kind of 3 areas that we're trying to teach together, and we kind of have different learning goals, and we need to keep these in mind. And they interact. So there's the computational thinking things, like, you know, interfaces, abstractions, specification versus code. There's the programming concepts that you need, and then the data structure and algorithms which you're trying to describe. So one example is when you talk about priority queues and restoring invariance. So you talk about what is a priority queue, how can you implement it with a data structure called a heap. And then on the programming side, you see that in some circumstances you can implement a tree as an array, which is not usually what you think about. You usually think about using pointers. And then the computational thinking idea is that for the data structure to work, it must satisfy certain invariant. When you apply operations, you will violate these invariants, and your algorithm is responsible for restoring them in order to get everything back into a good state. Okay, so looking forward a little bit, so contracts are currently checked dynamically, and they turned out to be extremely useful in the context of this course, just like they turned out to be extremely useful in Microsoft product development for probably related reasons. They bridge the gap from algorithm to implementation. They express a program intent. They catch bugs during dynamic checking, and they give you early failure and better localization of problems. And we would like to, in the sort of ongoing work, to exploit contracts further. So Jason, who actually just came in, we spent 2 summers at Microsoft working with Rustin Leno, is working on this right now. So a couple of directions we can take this. One is on static verification. So before you ever run your program, the system will tell you, right here, null pointer could be dereferenced. This is potentially a bug. Or it'll tell you this can't happen, and you have additional confidence in your code. And because of the simplicity of the language, I think we have a good shot at doing that. There are specific challenges if you try to do this in the freshman level setting. So it's not so simple. I mean, you can push out things to a large number of Microsoft developers. That's one has its own set of problems. But trying to make sure that students who are just starting to learn how to program and be think like computer scientists, to use certain tools has its own intrinsic challenges. But you also have an opportunity because every year you have 600, well, willing or unwilling subjects, okay, that you can try things out and you'll see what happens. They're also extremely diverse because they come from very diverse backgrounds, so you get probably a fairly good sort of a cross-section of the students who you want to address with that work. Okay, so to summarize, we have designed here with support from the Computational Thinking Center, the Principles of Imperative Computation course, which is a freshman level course, which emphasizes the interplay between computational thinking, algorithms, and programming. And the anecdotal feedback, like we haven't done any scientific study, is that it works. Works for the downstream courses. It also works in the sense that students do learn how to do these things. So if your final exam, you give them some piece of code, let's say you give them a sorting algorithm they have never seen, and you ask them to write the loop invariants, generally they're able to do that. Similarly, if you give them the loop invariants, they can write the code. So they do learn how to use these tools and techniques that we teach them. So the really interesting research question is now, can we use static analysis and theorem proving to, not for their own reasons, but to aid students in achieving their learning goals, make them better programmers. And inspiration, you know, so there's Mani Verdas, there's Peter Lee and Jeanette Wing, who, of course, were at CMU, now at MSR. Rustin Leno, who has been a very frequent collaborator. And we've had multiple interactions, people visiting back and forth, giving guest lectures on our course, or spending a summer at MSR. Okay, thank you.